Okay, welcome back. So now we will have a case study on a potential application of machine learning. You already been introduced to Mr. Varun Reja, our PhD student. So he will make a presentation of a particular application, that is laser scanning. So we will see some ways of applying machine learning for this scanning problem. So now I invite Mr. Varun Reja to make the presentation.
Hello, everyone. Thank you, Professor Benny, again. So I will just share my screen. Yeah. So hello, everyone, again. This is a potential. This is a case study on potential applications of laser scanning data using machine learning. So I thank IARC, IITM group plus National Supercomputing Mission for organizing this workshop. And especially thanks Professor Benny for taking this initiative to have this workshop. So I am a joint doctoral research scholar from IIT Madras as my home institute, and I am pursuing my joint doctoral at the University of Technology, Sydney, Australia. And so today we will see, first of all, what is the concept of laser scanning, some applications in construction where it is majorly being used, uh, use case basis machine learning methods on the spatial data that is obtained by laser scanners, and Scan-to-BIM, one of the particular applications where laser scanner is very much helpful, and what are the challenges and some innovations. So this will be the outline of the presentation. Starting with the concept of laser scanning, if you see on the right hand side, this is a laser scanner. This is a typical laser scanner. There are nowadays there are different type of laser scanners which are small in size, which are mountable also. This is a traditional laser scanner which is mounted on a tripod stand. The concept of a laser scanner is that it emits a laser beam, and the laser beam hits an object, reflects back, and it calculates the distance based on the time of light. So this is the concept, and it generally it uses more of the advanced sensors like GPS sensors, IMU sensors, to actually see from where the data has been taken, what is the motion of, if a laser scanner is mounting, what is the motion. And it also have cameras to detect, to capture photos of the scene. So if you generally have a mobile device, there will be an option for taking a sphere around you. So just imagine, instead of taking photos, the laser scanner takes photos as well as the points, and maps and generates a point cloud. So I'll just play a short video. This is a laser scanner which we took as a part of our IAC workshops, but I think this is pretty good to understand what a point cloud is and what are the different parts. So this is a scan view from screen recorder. Just see that how we navigate. So this point cloud was taken inside a classroom at IIT Madras. So as you can see, the laser scanner also takes the points which are outside the windows, because the windows are made of glass. So it takes trees and other objects also. But it is pretty, it captures the details pretty well. And you can actually, we have opened in Autodesk Recap, and we can easily remove the outlier points which are there. So this is inside of the classroom. The circle there, the sphere there indicates the point from which the laser scanner was kept, and we took the point cloud. So yeah, you can visualize in this way. And this is the lasers. So this was one view. This is called a scan view. Next will be so next will be the real view, which is taken from this. I am showing it from the perception of laser scanner. So it takes photographs as well as point clouds and it combines those both. So you can see there are some irregularities on the top of some disks, but this is how it looks like. It looks like a real image is captured and it looks very real. So the laser scanner is a very accurate device. When you talk about point clouds, it is better than other vision-based capturing device like photogrammetry, and you can see it gives a pretty real RGB data like textures, colors, plus the spatial data, the points. So what you can do, the basic things in recap is I'll just say you can take measurements directly. So this is how we directly measure using point clouds. So you just click on the distance tool in recap, and then you just measure from any point to any point. So it is very helpful for construction engineers to check whether the dimensions of the construction structure build are correct or not, whether they comply with the S design drawings or not. You can check any details. Right now it is the door width is 1.180 meter, and the beam width is around 350 mm. 350 mm. So this is how you take distance. So this is just a brief introduction about what point clouds are, how it looks, and what else you can do. So coming to back to what are the advantages of laser scanning over other methods. First of all, it collects the spatial data very quickly. Its accuracy is in MMs at 60 meter. Most of the laser scanners, which are a very high end, will have more better accuracy. Then it can be mounted to UGVs or UAVs, like grounded vehicles or aerial vehicles, and mostly for scanning inaccessible locations or hazardous locations. Generally, drone-mounted laser scanner is used where it autonomously goes inside the location, captures all the points, and it maps the data. So for deconstructing nuclear plants or underground tunnels where people cannot access, the scanner can be very handy to map the terrain or spatial space. Then the scan data can also be used for 3D modeling, which is one of its main applications. So for 3D modeling, we require 3D modeling means you have a point cloud and you generate a model from that point cloud. Okay, so the point cloud can be from any of the vision-based devices. Like you can use range imaging devices, you can use photogrammetry, but laser scanner is much more accurate. And it reduces manual labor to go manually and captures, because from one location it captures 360. Also, the instrument cost is very high for laser scanning. This is one of the disadvantages. Right now, the sensors are getting cheaper. So in near future, we may see laser scanners, but a typical laser scanner, which I showed you, cost around 60 lakhs INR at start. And a very basic one starts from around 30 lakhs. So you can see that it is not very, very cheap. So coming to what are the applications in construction particularly. So as I said, in construction, the lasers can be helped in design phase, the construction phase, and post life also, operation, retrofits, and renovation. Particularly for design phase, for 3D modeling, it is used to see the progress, to see if there is any to manage construction sites. This all takes advantages of scan to BIM. So the process of converting a scan data to a BIM model is called a scan to BIM. And this is like a pretty challenging problem in construction. And it has been taken up by many authors. We will see in the coming slides why this is challenging and how this has been tackled by some of the professionals. And in construction phase, We can have it in to detect clashes by mapping the point clouds. We can see, you can use it for progress monitoring. We can use it for progress visualization. We can use the 3D data for progress visualization. There are many softwares which gives a very good visualization of which components of the project has been built, which are not built. And for retrofits and all, generally these point clouds are taken for constructing the as-built records. So if a construction facility is already built and you don't have a BIM model for it, you take and scan the particular building or archaeological site, and then you monitor it. Like you can do structural health monitoring or many things you can do with the point cloud data. So coming to the main problem, which is the scan to BIM. So once we have a scan data, the challenge is to convert into a BIM data. So as I said, you can use laser scanners, sensors, depth cameras, but the laser scanners are more accurate version of it. And currently, for digital modeling, what you capture from site is called as an as-is or an as-built BIM model, and which is planned, which engineer makes before the construction starts or in the design phase, is known as planned model or as designed model. So this is how a point cloud looks like, and this is how a converted BIM looks like. So there are various automated methods of converted point clouds to BIM, and they use some kind of learning-based techniques, which Professor Benny might have already talked about in his this workshop, and maybe in the next sessions he will be talking about. So those techniques will not be talked over here. This workshop, this session only talks about how laser scanners can take up those techniques. So for example, segmentation. You have a laser scanner. So this is a typical laser scan data, which is segmented. So the pipeline for segmentation starts from acquisition. And when you extract the data, then there is a process called as point cloud registration. So what registration is when you have a laser scanner scanning through a multiple locations. So at the end, what you have to do is you have to combine the laser scan from all the locations. So how you do the registration, you can do it automatically and or you can do it manually. So there are various techniques in automatic and manual registration. So manually, you will have to select at least 3 points and overlay over the other laser scan data and fit it in automated processes. We have more advanced algorithms like iterative closest point algorithms, which minimize the distance between the two laser scanning data, and it minimizes the point distance, which are the common points. It minimizes the distance. There are some more which are manual methods and semi-automatic methods, like you place a marker on the wall, you you scan the room, and then you scan the room again from a place where that marker is visible. So that marker becomes a common point, and then you match that marker geometry to get a match between the point clouds. So this process is point cloud registration. Then comes the outlier removal. So if you remember, I showed you the point cloud where the data outside the room was like having trees and all. The points came from the trees. Those are outliers. Those are like the points of no interest. So that can be removed using techniques for outlier removal, and we will talk about that also. So once you have a standard input point cloud after getting the pre-process, these are all pre-process registration, outlier removal. These are all the part of the pre-process. Then you do point cloud segmentation. So segmentation is like you have to make point cloud into clusters or classify point clouds based on features, and then you have to make patterns or groupings and segment the point cloud. So let's say you have this point cloud. So this point cloud will be clustered so that all the points which are of same type or having same features will be at one plane, and they will be color coded differently. So this technique is known as segmentation. So this uses classification and clustering algorithms. And so coming again to processing, processing is if you have a point cloud data, you pre-process it, like you augment it, densify it, remove outliers, and then you apply techniques like object detection, segmentation, classification using learning-based methods or deep learning methods. Starting from pre-processing. So, excuse me, yeah, starting from pre-processing. So this is a part of the point cloud which I showed earlier. So in this, there are many what I will say ambiguities, or we can say things which are of no interest, starting from noise and clutters. So there are few points which lie outside the region where there should not be any point. This happens because of some reflection from air or something, but these points are called as noise point. So these noise has to be removed. Then outlier points which are of no interest like trees and all has to be removed. Then there are some gaps which occur because if a laser scanner is only placed at one location, you won't be able to capture point which are behind it. So those are known as gaps and occlusions which hide behind. So you have to take scans from multiple points to fill those gaps to get a perfect point cloud. So machine learning can help in clustering these points. So if you take a wall and if you cluster the points of the wall, then the outlier points will automatically not be clustered. And we can use many clustering algorithms like DB scan. It is density based scan and k-means clustering algorithm and nearest neighbor algorithm. So what it does, if you can see in this diagram, there are two clusters and the green points are the outlier points. So it makes those cluster, and you can easily remove the outlier points when you have run those algorithms. As I already told about point cloud registrations, uh, it aims to find a rigid transformation to align one point cloud to another. So you have manual based techniques, marker based techniques, and feature based techniques. So in manual based and marker based, I have already explained. In manual based, you have to select at least 3 points from both the point clouds, and they will overlap one another. This is more of a less accurate technique. Then comes the marker based techniques where you paste markers or signage on the walls, and then it aligns based on those markers. Feature based techniques is advanced techniques which used deep learnings to extract the features from the point clouds. Like the two point cloud, it will extract the features and it will match the point clouds based on those features. So you input the features based on multi-level perceptrons. It will find those the global feature vector, and it will finally register the both point clouds. So coming to back to our problem, which is Scan-to-BIM. So how manual Scan-to-BIM is done? So this is manual Scan-to-BIM is done based on you have a point cloud and you overlay it in a planar mode, and then you select the walls, you draw walls manually. So this is a very tedious process. So people have made researchers have made some plugins. This is a screenshot from plugin called as Edgewise. So it helps you to detect wall automatically, but it won't convert the full point cloud directly to a BIM model. So these types of plugin are like semi-automated methods of scan to BIM, but we need a more automated method. So just a brief about how the scan to BIM works in a conventional way. You scan a point cloud, then you take the point cloud into a Revit environment or any software which supports point cloud. Then you draw wall geometry one by one with the help of any tool such as Edgewise or something. And then there are some few more tools which can detect windows and doors. So once those are detected, you can delete those components and there will be gaps. And then after a long manual process, you come to a finalized BIM model. So this actually works. The conventional method works if there is a small model and you don't have any scan to BIM automated techniques. Also, there are some constraint based techniques, like if you have to detect walls, then you can give some constraints like the wall will be a particular perpendicular to the floor, or these type of heuristics based constraints you can give. but this does not work for all elements. You can give dimensions of the wall also, that any point cloud which is having a gap of 200 can be detected as a wall, but this does not work for all elements. So in construction, many elements are unique, and hard coding programming is required for all the projects. Hence, we tend to have a learning based approach where the features are learned from point clouds, and then we have an automated method of Scan-to-BIM. So this is the workflow which we developed, and you can this I have just put to just to show that how many machine learning methods can be there. So starting from data acquisition and transforming, we can use registration in outlier removal, and sorry, we can use machine learning in outlier removal, as I told. We can use it in registration and alignment of multiple. It can be done by classification and clustering techniques. After that, once the point cloud is there, we can do object identification using pattern recognition. So all of these techniques which I have shown in this flowchart uses some or the other kind of machine learning techniques. So so this is the paper we presented in International Conference on Pattern Recognition this year in January. So the segmentation is like this. If you see, all the planes are separated, and once the planes are separated, you do geometry development, automated geometry development, and automated geometry development can be labeled and separated by BIM model. So this is geometric modeling and IFC assignment. So apart from geometric modeling, if you want to give texture and detect the material type, you have to learn from the point cloud RGB data. So both techniques can be applied, heuristics based or learning based techniques. So what is geometric learning? Geometric learning learns from geometric features, generates a feature vector, matches that feature vector to the training data, and classify and label the point clouds, and replace the points cloud with corresponding IFC element. So it is some kind of like this only. First, you segment the point cloud, then generate features vectors of these clusters, and then convert it into a geometric model, and then replace it by an IFC element. Similarly, appearance-based learning, you segment the point cloud and obtain textural color features from the point cloud data, the RGB information which the point cloud have, generate a feature vector, and match the feature vector with the training data, and classify operational state of the element. So, Hitesh, your speaker is on. Can you just turn it off? Hitesh? Yeah. So challenges for learning-based methods are for learning-based, we require an extensive point cloud training dataset. There are unique elements. Excuse me, Hitesh, can you just? Benny sir, can you just mute him?
You can mute him.
Okay, thank you, sir. So challenges which apply for learning-based to applying learning-based techniques are, first of all, learning-based techniques require an extensive data set for point cloud training. So generally for construction, we don't have an learning data set as of now, which have point clouds of columns, point clouds of beams, which the features can be learned. And there, as I told, in construction, there are many unique elements. So it is difficult to get training data for all the elements, and the computational requirements are high to process such large kind of data. Each project is different, so we can't apply the same data set to every project, and open source and benchmarking will really help, but this is not happening now. So the people have not open sourced their point clouds data so that we can generate a large training data set, and benchmark how these training applications work. So in that paper which we presented in ICPR, we gave an method to how to generate a label training dataset easily. So I'll just give a brief about how that method works. So we have this point cloud which we take from a site, and we overlay it over a using a VR device or a AR device. If we are using a VR device, then we overlay it over a BIM model. If we are using an AR device, we can overlay it on a real site. Okay, and then a particular user can wear VR or AR headset, and the user interface we made was such kind that once the point cloud will be laid over it, the segmented point cloud will be laid over the model. The user can select which point cloud it is. So if this point cloud is laid over a BIM model, user can select where are the pipes, where are the walls, where are the beams, and he can manually feed in the data using directly AR and VR visualization. So so for automated extraction of point cloud parameters, we can have manual feeding through data feeding process, as I already told, and the feedback is very interactive. You can select what type of element. There will be like a drop down list in front of an element. You can select that, and that uh, point cloud will be labeled. The part of the point cloud will be labeled. So finally, you will get this kind of interface where you have a building, you overlay it, and you can select which kind of element is this, which kind of element is this. So it is a pretty easy user interface to use. We are actually working on development of it for the next phase for implementation. So that's it. Thank you. If you have any questions, I will be happy to take.
What is the last slide which you showed? Which software is it, or is it inbuilt by you and?
Yeah. So this is we have made it using Unity. Unity 3D. It is a gaming software. So in gaming, as you can see, we have very much I will say options to explore point clouds. I will say, because gaming uses first of all high visualization for visualization tools, as well as high mobility tools for that visualization. So in this point cloud, if I want to enter this room and stand inside this room, Unity does that for me.
Okay, thank you. You also mentioned that it has a point cloud generation and the complete processing and everything. Okay, especially processing.
Just a minute, I could not hear you. Can you be a bit loud, please?
Okay. Am I audible now to you?
Yeah, you are audible now.
Okay. You mentioned in your presentation that the high computation cost is there. Does this point cloud processing especially, does this require GPU and TPU?
Yeah. That is exactly why one of the challenges in using learning-based techniques or using point cloud data. So the point cloud data we generally get from site is not in MBs, it is in GBs. So just for a building, the point cloud data can go in GBs. So either you downsample it to reduce the processing. Downsampling means reducing the density of the point cloud. Either you downsample it or you run it over high-end GPUs to do the processing. So I'll just give an example. I'm running a code for segmentation from yesterday morning, and it is still running. I'm just saying it is on the 41st iterations. So it is running, it is running since yesterday morning, and I couldn't get the output. So it requires very, very long time to process these data. So high-end GPUs will work.
Okay, thank you.
Yeah, thank you.
Hi, Varun sir. With respect to structure health monitoring, since the data is so large, will it be useful in finding minute cracks in the building? Or
Yeah, good question, Rajul. Actually, I also initially thought that how can laser scanners be so accurate that they detect cracks and they detect cracks in buildings. But but strangely, it is being used. They have a very high accuracy. You map the building, you will get points inside the building. If with a laser scanner, you can even mark the profile of the crack. So I was also surprised, but that is how laser scanner is being used.
Okay, thank you.
Yeah, I
And
think
since you have
detecting.
since you have experimented this thing, so can you highlight the cost? Let's say if you start some project, and what are the cost involvement and the time taken to compile all this data and get the results? For example, the
Okay.
scanner. For example, the processings. For example, the other factors which you have incorporated. So, what is the cost involved?
Yeah, I understood your question. Just Professor Benny, you were saying anything? If you want to go ahead.
No, I wanted to just add to what the previous question for detecting cracks. We can use close range laser scanners. People have used, so what Varun has shown as long range one to capture big objects like buildings. So there are laser scanners which work at a much closer range, and people have mounted these on drones, and you can move it along the, for example, you want to inspect a beam. You can go very close to the beam and you can record it. So there are some research papers where people have done this type of crack detection using laser scanning. So it is possible. It's not mainstream yet, but people are already working on things like that. Varun, you continue.
Right. So I'll just answer that question. Right now, the laser scanning technique is just spatial data is being mostly used for visualization at sites. So right now, I have not seen sites use it much for scan to BIM in India particularly. The laser scanner cost is very high. So few companies are able to afford it, but those who are able to afford it, they are using it to map the terrain. So we did an initial survey of how the vision based devices like photogrammetry and laser scanning are being used, and it is very shocking to see that we got from 200 response, we got 0 responses for the use of laser scanners. So I'm pretty sad to say that it is not being used very relevantly in the constructions industry, but for advanced operations like archaeological mapping and all, laser scanners are like the must need. They require laser scanners to map the existing building. Now coming to the second part of your question, if it will be used, what will be the computation cost and how it can be implemented? So first thing, the laser scanning data is of huge quantity. We will require high-end devices, first of all, to store it and process it. We will require maybe high-end GPUs to store it and process it particularly on day-to-day basis. So if you are using laser scanning for progress monitoring, you will have to have a dedicated computing facility either remotely or on site for it. If you are having remotely, then you will also have to worry about the data transfer and how you will do the daily data transfer over it. So those are some challenges. I cannot give a particular value to the cost, but I will say initially it will be high, but on a long term, it will you can see the benefits of doing that kind of thing because you will get an exact data.
Hello, Mr. Varun. This is Jay Chandran. Just wanted to
Yes,
add
yes.
that in India, L&T has used laser scan to BIM
Right.
in a full-scale facility where we were to revamp factory. As-built drawings were not available. It was an industrial facility, material processing facility. Then we scanned the entire facility. So all the equipments were scanned, it was converted into BIM model, then the re-engineering revamp was planned. It's applied
Happy to know
successfully
that,
done.
Jachandran. It is very happy to know that because in our initial survey, that thing was not reflected. I would like to know the details of the project if you can mail me. Okay, I will.
Oh, yes, we can connect.
If you can
offline.
connect.
We will do that.
Yeah,
Yeah.
we can connect.
Currently,
Sir,
yeah.
if you can.
Definitely,
Right.
definitely.
Thank you for that input.
We are
Sure.
also kind of piloting something to do progress monitoring in some of the facilities using laser scan to BIM. We are using it to see whether we can use it for, especially for finishing works and other. Also, we are kind of piloting some of the initiatives. We can share that.
Okay, so that is like the core part of my research, my PhD research. So I would be happy to connect. Yeah.
Okay, thank you.
Thank you for that.
Will your this presentation be available?
The recording of this will be available, right, Professor Benny?
Yeah, recording will be available. It might take a couple of days, but it will be available. Yeah.
Hello, Varun. Hello. Hello.
Yes.
Yeah, Varun, can you explain how these patterns are recognized? Like what type of patterns? Like I understood the clustering part, grouping and all, but the classification algorithm part I did not get. Like what type of patterns you can explore in this type of projects?
Right, sir. So, sir, the thing is, we have all of the point out data works based on features. So the machine recognizes the feature vector, and the feature vector actually is based on a number of features that the one of those can be patterns. So if we are not able to see those patterns, the machine is able to see those patterns or recognize those patterns from the point of data. If Professor Benny can add something which I am missing.
Okay, I can explain with example. In this case, pattern you mean say like you generally go 0 or 1 or
So
pattern
means if machine sees RGB data as a pattern, like the wall is of pink color and let's say the column is of blue color, let's say, just assuming. So when it sees the pattern, it recognizes those RGB patterns from the data and classifies based on those features. So in this case, RGB data have given a pattern to machine to recognize those data.
Okay. It depends upon it's a project specific. I mean.
Yeah, it is actually not project specific. It is actually feature specific. What kind of features the algorithm is going to learn.
Okay, fine. Thank you.
Yeah, thank you.
Good afternoon, Varun.
Yeah, hi.
Varun, what are the features which will be like encapsulated in this point cloud? I mean, the XYZ coordinates will be there, obviously. And what are the other parameters it will encapsulate within it?
Nandish, what I'll just tell you is there are two kinds of features. Either you can provide the feature manually. Okay, so manually, what we can provide is we can provide the X, Y, Z coordinates. We can provide, let's say we have a beam, we can provide if you want to learn, let's say this wall which is there on this compound, you can provide what is the X extent of this wall, like the length in X direction, length in Y direction, length in Z. I am telling about learning point clouds, not learning points features, learning point cloud feature. So you can give those data. You can give if you have already the surface area of the training data, labeled training data. If you have a surface area of labeled training data, the volume of labeled training data, you can give those. So once you give these features, if another wall you want to compute, okay, you have given an input features for this and this three walls you have given input features. And if you want to compute from a point cloud, what element is this? It will take those things into account, the surface area. But if you use purely deep learning algorithms and you don't give any feature for this manually, it will take advanced features like shift features and surf features. Yeah.
Okay. But inherently, it will not recognize. It will recognize only points, and only through these algorithms it will be tagged about its other parameters.
Yeah, it will be labeled. Right.
Yeah. Okay. Thank you.
Hello, sir. Sir, you did the classification by the cluster. So clustering based, right? So shall it possible to classify by the XY plane? Like when we do for the crack detection, in that we require higher accuracy. If we go by the cluster, then we somehow reduce the accuracy part. So if we want to do the more accuracy, then we will classify by the XY planes and the label all of the data like the wall and the crack. Can it possible to distinguish by that?
If I understood your question correctly, you said that you will classify based on planes, right? XY plane,
Yes.
YZ plane, ZX plane. Yeah.
Yes,
So
sir.
Nikon, you can do that, but the thing in that is that we have already tried it. That if a element is not aligning to any plane, which is particularly random, like a slanted wall is there or a curved wall is there, it will not work in that case. So that kind of that what you are telling is like a heuristic based method, that the floors are always horizontal and they will be particularly in YZ plane if there are. Yeah.
Yes. But sir, for the crack, apart from the cluster base, which are the other things we will try? Like, I'm also working on the
Nikun,
same
when you said
area.
for cracks, we will use close range laser scanning. So that will actually profile the crack. Profiling the crack means it will actually tell us how the depth is, what is the shape of the crack, and everything it will tell. So generally, drone-mounted lasers, close-range laser scanners are used where they have a camera plus a laser scanning system. So with the camera, you can detect the cracks on the go, and with the laser scanner you can actually scan their profile, and after that you can actually do a detailed analysis of what is the cracked width, how deep is the crack, that all.
But sir, these will be the manual approach, but I am talking about the automatic approach. Once we
Yeah,
are having
so
a exact point cloud,
so you want automated crack detection, right?
yes, sir. Means
Okay, so
we
there
are
will be
having the
methods
dense
for it.
point cloud.
Okay, so there will be methods for it because that is not my core domain. I'm not aware of that.
Okay, sir. Thank you.
But there is one question.
Yes, sir.
How SCANA is used to convert the design BIM model to real construction?
Means the design BIM model.
Uma, can you explain your question?
Actually, for now, I have to say a building I have to construct. I have created the BIM model for that, and I want to. How will this scanner be used for stage by stage construction? Whether it's as per
Okay.
the BIM model.
Okay, so what you can do is for monitoring purpose, for deviation detections for monitoring purpose, you can take the real site scan and overlay it on the BIM model you have already created. So there are softwares like Cloud Compare, there are softwares like plugins in Revit, which tells you how much the construction which you have done actually on site, which is in form of a point cloud, is deviated from the BIM model. Let's say a column is tilted with 1 or 2 degrees, it will automatically show it as a red component, that these points of the columns which should be inside or which should be in the boundary, like outside the boundary or are not aligned. So in that case, you can actually use it. You can also use to detect progress, model-based progress detection you can do. If that answers.
Yeah, you need to go one step beyond BIM. You have to go to 4D.
4D.
So some of my students are currently doing this. Creating a 4D model with the time also.
Time also. Yeah, we know that.
In the model. So at any time, what is the planned the model, and then you, as Varun said, you can overlay it with what exists on site, and then you can compare. So one is this fault detection, as Varun said, if a column is tilted, by comparing with the BIM model, you know that there is a deviation from the model. The other is looking at what was planned for that particular date, and comparing it with the actual one. So you can see these columns should have been there, but it's not there. So progress, it's not up to schedule. There is a delay in the work. So these kind of analysis could be done.
Yeah. Okay.
Thank you, sir.
Yeah, thank you.
Are there any more questions? Okay, thank you, Varun, for this interesting presentation. I see a lot of discussion, a lot of people are interested, so it is really good. So thank you once again.
Thank you, sir.
Thank you, sir.
Again, I would like to thank to give me this opportunity to present in this workshop. Yeah.
Interesting and informative. Thanks, Varun.
Thank you, sir.
Okay, so we will just take another half an hour more and then we will break for lunch. So we'll continue with the lecture. I just quickly go through what you wrote about this polynomial generalization. So the question is, I'm not sharing my screen. Maybe I'll still try, and after that I'll shift to the other the computer. Let me just share my screen. Just a minute. Right. Yeah, we discussed this already. Yeah, we discussed this already. 1 second. I think selected the. Okay, by the way, I have uploaded the Excel file on the workshop website, so you can download it from there. This lecture note is also uploaded. Okay, so we were discussing about the Rosenblatt's perceptron algorithm. Sorry, I got confused. So let me come back to the exercise. You're able to see my screen, right?
Yes, sir.
Yes, sir.
Yes,
It's here,
and the voice is also okay, right? I'm using 2 different computers, so that's why I'm a bit confused. Okay, so the why does the updating procedure work in the perceptron algorithm? Yeah, what I expected you to write is what is that specific meaning of that rule which is applied, that particular equation. Okay, there are some people who have written it correctly. So there is a prediction error. So correct the error by incrementing the value of W using the learning rate. Okay, there is another one, the value eta times yi times xi increases the value of wx plus b by a small value, so it can become equal or greater than. So some people have tried to understand the meaning of that equation and try to answer. So there are some answers which are correct. So if you look at, so now I'm going to share this is the presentation. 1 second. Okay, so if you look at this expression, if it is less than 0, it means that there is a misclassification. So let us say yi is positive, actual value is positive, and the predicted value is negative. Wx plus b is negative, so there is a misclassification. So you want to increase the value, the predicted value, so it becomes greater than 0. So W is increased according to this. Y is already positive. So if you increment it like that, you will see that eventually the value of the Wx plus B becomes positive. So the whole thing becomes positive. So there will be no misclassification. Similarly, you can see if yi is negative, similarly you decrement it. So the product becomes positive, eventually it gets classified correctly. And the actual reason is you can show that even if you do a gradient descent in optimization, you get exactly the same equation, which will reduce the classification error. It was proposed as a heuristic based on the performance of the human nervous system, biological nervous system. The idea is that you strengthen connection which are already strong. So if you have a high value for xi, you increment that further. So it is based on some analogy with the performance of the biological nervous system. But you can show that even if you do a gradient descent, you get exactly the same formula. So you provide an increment to W in the direction in which it reduces the misclassification. So basically that is this Rosenblatt's perceptron algorithm is one of the heuristic. Now we move on to the next algorithm, that is an artificial neural network. Is undoubtedly very important because today if you say you're working on machine learning, people will automatically assume you're working on neural network. So it's so popular and is almost synonymous with machine learning. And even the latest developments like the deep learning and all that, they are just a neural network. Is a more deeper form of neural network, a neural network with many layers. So it is important. So we try to understand this in more detail. So as I said, it is inspired by biological neural network. A neural network consists of a number of neurons. So it looks something like this. So this circle you see at the center, that is a neuron. And you have number of connections, number of nerves that are connected to it. So we have, I've shown 3 input nodes connected to the node J and 1 output node. So a neuron receives input from a number of incoming connections, and you have a number of outgoing connections also. And the output from a neuron is a function of the sum of all the input. So the neuron is receiving input from number of incoming connection, and the output from the neuron is a function of the sum of all the input. It need not be a linear function, it can be a non-linear function. Today people use sigmoid function. Sigmoid function is very common. It's a sigmoid function, and in the olden times people used a threshold function. Threshold function is not that popular today because of a lot of issues with optimization. I'll explain that later. But let me explain what how it works. So you have neurons, you have a network of neurons. So you have each neuron receives input from a number of other neurons, and they are interconnected, and the net output depends on the strength of connection. We'll take some examples, it makes it very clear. So it looks something like this. We arrange all the neurons in different layers. We have an input layer which represents the input variables. We have an output layer which represents the output variables. And you might have one or more hidden layers. I have not shown the hidden layer. So this is how a network could look like. So if you want to predict a particular output variable, if you know what are the input variables, so you form a network consisting of one or more nodes in the input layer, and you have if you have one output variable, typically you have one output node in the output layer, and you might have one or more the hidden layers with many neurons. So this is how it would look like. Now a 4-layered network consisting of 2 hidden layers, one input layer and output layer. I've shown something like a fully connected network, and depending on the application we might decide on the topology, how the nodes are connected. So you can see here the input layer consists of 3 nodes, and in the first hidden layer you have 4 nodes, and they are all connected to each other, and each connection has a strength. We call it as these weight factors W1, W2, W3 and so on, and the net output from the network depends on the strengths of these connections. We look at the mathematics in a short while. So this is how it works. So you have some input nodes representing the input variables, and there is output from each of these nodes in the input layer, which go to the next layer. So this node receives input from these input nodes. Similarly, this also receives input from this, and the input received at this node is a function of the weight factors, the strength of these connections and so on. So the net output which comes out of the network depends on the weight factors, the combination of weight factors. We'll take this simple example to understand this. So you have 2 variables, x and y. So you have 2 input variables, x and y, and the output variable is z. And we want to find out what is the output that comes from this output node. You don't have any hidden layer. This is a simple network. And each connection, each edge has a weight factor, W1 and W2. You have 2 edges. The simplest output function is an identity function. Identity function is whatever is the input is the output. So let us say we have this node Z, which has an output function, which is the identity function. So the net input received by this node Z is proportional to the weight factor. So whatever comes from the node X multiplied by W1, that is the input coming at Z through this edge. Similarly, from the next edge, we have W2 multiplied by Y. So the net input coming at this node is W1X plus W2Y. And if it is an output, the identity function, the output from this node is exactly equal to W1 times X plus W2 times Y. So you can see that it is exactly the same as what we saw in the regression, linear regression. The Z equal to a linear combination of all the input W1X plus W2Y. Now, in general, we might also use a threshold function. The output is, there is no output unless the net input is greater than a certain threshold. So let us say we have a certain threshold T1, say 0.5. If the net input is less than 0.5, the network doesn't produce any output. The node doesn't produce any output. Otherwise, there is an output. And there are also, you also see terms like ReLU, rectilinear, linear, the unit. So these are, so you might have functions like, if the output is less than a certain threshold, the input is less than a certain threshold, there is no output. After that, it is proportional to the output and so on. So there are different types of output functions that are possible. We'll take this simple example to understand this. So this is that, I think we covered it in this example in one of the lectures before. So this is for selecting a slab system for a building. So you have different options depending on the parameters, whether it is a large span whether the shape is square or rectangle. So we have, I put 4 nodes in the input layer: large span, small span, square, and rectangle. Imagine all these are binary variables. So if it is a large span, we put one value of 1 to large span and small span equal to 0. With a small span, you put large span equal to 0 and small span equal to 1. Similarly, if the shape is square, you put 1 at this node and 0 here. If it's a rectangle, we put 1 here, 0 here. So we can treat all the variables, convert everything into binary variables and these can be represented by the nodes in the input layer. And the output layer, we have multiple labels, whether it is a one-way spanning slab system or two-way spanning slab system or a waffle system. And depending on what is output at each of these nodes, we interpret that as the slab system we use for the building. Okay, so we'll now do this simple exercise. I want you to find out what will be the slab system when it is a large span and a square shape.
Hello, sir.
Tell me.
Sir, how we distributed the weight?
Weight I have manually given. In a real neural network, we have to learn the weights, just like we did earlier for other kinds of learning. For example, for linear regression, we had an optimization problem which will give you the weights. But right now, for this example, I've already manually given you the weights. So from large span to one way, the weight is 0. Large span to waffle, I've given the weight as 1.0. So I've manually given this just to understand how the network works. So using this, I want you to predict what will be the slab system when the input is a large span building with square shape.
It's a step output, sir. For example, 0, then we have 1, then we have 0. So step unit function is the output for large span and square.
Okay, no, you assume that it is the identity function.
Correct.
Whatever is the net sum of input, that will be the output.
Right, sir, right.
Anybody, what will be the output when it is large span and square shape?
Waffle, sir.
Okay, so if we look at the output from each of these output nodes, let us take this node. See what you get. From large span, the weight factor is 0. So 0 multiplied by 1, that becomes 0. So there is no input coming from this. Small span is 0. So again, this is 0. Square shape, it is 1. Value is also 1. So you get 1. Like this, you can calculate what is the output from each of the output nodes. So typically, if you have a network like this, we say we compute the output from all the nodes and we can treat it as some kind of a probability. So the one which has the highest value will be the output. So if you look at large span and the square shape, you will see that this has the maximum output. You get an output of 2. So we can say the output variable is that is the slab system as waffle in this case. So this is just to give you an idea about how the network works. Now in reality, it is not an identity function. You might also use a threshold. So in this case, we might say if the output is less than 1, if the net input is less than 1, if you set the threshold as 1, if the net input is less than 1, there is no output. So all these nodes, one way, two way, all give 0, and the waffle will give 1. So we can also use the threshold function. Okay, so to come back, the artificial neural network consists of number of neurons. You can have one or more hidden layers. You can have an input layer, output layer. Input layer represents the input variables. Output layer represents the output variable. And the hidden layer represents nodes, which shows interrelationship between the variables. And the output from a neuron depends on the weighted sum of input coming from all the connected nodes. And the output function can be an identity function, It can be, you can use a threshold function, or you can use functions like linear, rectilinear output. And we can also use nonlinear functions like the sigmoid function. Okay. Any questions so far about neural network?
Sir, if we will have more and more hidden layers, our accuracy will increase.
Right. Okay. So we are going to do some exercise which will bring this out. Whether the accuracy will increase or decrease. We will see. We are going to do some exercise. It will become clear.
So can you give us one more example?
Yeah.
Can you give us one more example, like which is a little more complicated, so that we can understand?
We are going to do that. So let's do this exercise. We will do this exercise so we can find out how this network actually works. So I plan to do it later, but since you asked, let us do this. So I've shown the network consisting of 2 nodes in the input layer. We have 3 nodes in the hidden layer. We have 2 hidden layers. So this is the first hidden layer. This is the second hidden layer. So we have 2 hidden layers. In the first hidden layer, we have 3 nodes. In the second hidden layer, we have only 1 node. I have deliberately chosen this to make the calculation simple. In a real network, we don't just arbitrarily assign a number of nodes like this. There's some consistency. So you can assume that there are other nodes in the hidden layer, but they have 0 weight. So just assume like that. This is only to simplify the calculation. So normally when we say we have 3 nodes in the first hidden layer, 3 nodes in the second hidden layer. We don't arbitrarily choose the number of nodes in each layer. There will be some consistency and some regularity. But for this example, assume that this is the network and this is how it is connected. And I have given you the weights like before. In reality, it will be learned from data, but now I have manually given you the weights. So let us see what is the net output from the network. I'm also using a threshold function with a value of 0.5. And the actual exercise is to predict what is the relationship represented by this network. But I'm just modifying this exercise for your practice, for your understanding. So I want you to predict what will be the output if x1 is equal to 1 and x2 equal to 0. So you go through this network at each node, you find out what is the output, and tell me what is the output you get from the node Y. Okay, so this will give you some idea about how the neural network works. And imagine all the hidden layers have a threshold value of 0.5. So unless the net net input for that node is equal to 0.5, there is no output. It will become 0. If it is more than 0.5, the net output will be equal to whatever is the net input. Okay. So we are using a function something like this. So if the net input, we call it as the activation level. So if the activation level is 0.5, less than 0.5, there is no output. So I'm plotting what is the output as a function of the activation level. So activation level is 0.5 or less, there is no output. Otherwise, there is a linear output. So we use a function like this, and I want you to predict what is the output from this neural network when the input is x1 equal to 1 and x2 equal to 0. So you want to predict what is the output from the node Y by going through this network. Do this calculation. It will take some time, but just complete it. Maybe you can do it during the break, so you can understand how the network works, and then we will continue. Any questions? We'll come back to this example after the break. You can do it, complete the exercise during the break, and then we will. Okay, so I'm going to stop now. We will take the break. You can complete this exercise. And after the break, we will start at 2 o'clock.